Hi everyone, and welcome back to The Power of Reason. This is the 9th episode of this series, a very important and kind of a tricky one. I will introduce the concept of Bayes' rates, which probably does not sound that exciting, but it does have far-reaching implications, and it will help us define good and bad stereotypes and adjust our judgment accordingly. I guess that at this point, if you're watching this series, I don't need to sell it to you. The best approach is to jump straight into the thick of it. So, hydrate, do whatever you need to do to stay focused, and let's go. What is a Bayes rate? As always, let's start with a simple textbook definition. A Bayes rate is the general probability of something, or the percentage of a population with certain characteristics, when no additional information is provided. For example, if 5 in 100 cars out there are red, the Bayes rate for red cars is 5%. If we were to pick at random a car from all cars in the street, we know that the probability of it being red is 5%. So 5 in 100. Please be reminded that a probability is the likelihood of something happening, where 0% means no chance and 100% means certainty. Next example of a Bayes rate. If 1 in 1,000 people show side effects for a new drug, the Bayes rate for the drug's side effects is 1 in 1,000, or 0.1%. If we give the drug to a person at random, the probability of them showing side effects is 0.1%. So far, so good. But why do we need to know about Bayes rates? Because ignoring them, as usual, can lead to seriously wrong judgments of probability. Let's see this in a bit more detail. Assume that 1 in 1,000 drivers are currently drunk. So, the Bayes rate for drunk drivers is 1 in 1,000. Or 0.1%. This is just a fictitious example. Consider a breathalyzer which never fails to detect a drunk person, but it does display a false drunkenness in 5% of the cases, when the driver is actually sober. These are called false positives. Assume that the police are out on the street and stop one driver at random and perform the breathalyzer test. The test shows that the driver is drunk. My question to you is, what is the probability that the driver is actually drunk? Most people will intuitively say a high percentage, up to 95%, thinking about the 5% false positives. But the actual probability of the driver being drunk is only 2%. This is because there are so many more sober people out there than drunk people. That is the Bayes rate that shouldn't be neglected. Only 0.1% of drivers are drunk, or 1 in 1,000. When testing the only 1 in 1,000 who is actually drunk, the result of the test will be positive, of course. But when testing the remaining 999 people, 5% of the times, the breathalyzer will display a false positive. So, about 50 people in 1,000. Therefore, only about 1 in 51 positive drivers is actually drunk. So, 2%. Now, false positives are a problem, mainly when dealing with the low incidence population. Imagine a test for an infectious disease, which never fails at detecting a positive, so if someone has the disease, the test will definitely show it. But it also has a false positive rate of 5%. So when testing someone who does not have the disease, 5% of the times it will show that they will have it, which is a false positive. Same as the breathalyzer example, exactly the same. When testing someone at random and they test positive for the disease, the probability of them actually being infected depends on the incidence of the disease in the population, or the base rate for the disease in the population. If 40% of the population are infected, so we are assuming a base rate of 40%, then the probability that a positive test is actually positive is 93%. I'm not going to work out the math. So it's reasonably accurate because 93% of the times the test is accurate. But if only 2% of the population is infected, so now the base rate is 2%, not 40%, the probability of someone being actually infected when the test result is positive is only 29%. So it's rather unreliable. The reason for this is that when there are so many more people who are not infected, the false positives will statistically outnumber the true positives. So the reliability of the test depends on how many people actually have the disease. This seems like a counterintuitive effect. The reason for this is that we tend to intuitively ignore base rates and use the more specific information, which appears more relevant to our mind. So, if you think you can have an intuitive understanding of how statistics work, well, you have to think again, I think. This is especially true when the base rate information does not appear as representative or causal, while the more specific situational evidence does. If you watched the previous episodes of this series, you will know what I mean by representative or causal. And if it still sounds like utter jargon, then maybe an example will make it all better. In a small rural village, a hypothetical village, the most common profession for men is farmer, with 400 men, and the least common is librarian, with only 2 men being librarians. So 400 farmers and 2 librarians. Adam, who lives in the village, is a meek and tidy man with a passion for poetry. Is Adam more likely to be a farmer or a librarian? Does this sound like a trick question? Had we not been given the description of Adam, if he was just someone at random, it would be easy to know the probability of him being a librarian, just enough to do 2 divided by 400, which is 0.5%, which is the base rate of librarians per farmer in the village. Which also means that Adam would have a 99.5% probability of being a farmer, if it was just picked at random. But we have been given some information about Adam, his description. Adam really closely fits the stereotype of the librarian, and it forms a coherent story in our mind to think of him as a librarian. In light of this, the fact that there are way more farmers in the group, which is the base rate, seems irrelevant. However, thinking intuitively and ignoring the base rate will lead us to inaccurate predictions. At the same time, it seems harsh to ignore what our common sense is telling us altogether, and to just say that the probability of Adam being a librarian is 0.5%, as if we had not been given his description. How do we solve this conundrum? In light of all of this, both the base rate and the specific information should be integrated in order to formulate our final judgment. Now, in order to more accurately calculate how likely Adam is to be a librarian, we can make up some assumptions. Assume that we are very sure that the description of Adam fits a librarian and not a farmer. To put it in numbers, we can say we are 90% confident that the description of Adam is that of a librarian and not of a farmer. We can't say 100% because, after all, it is more than possible for some farmers to be meek and tidy and to love poetry. But we're just using a general stereotype. By saying we are 90% sure of his description, it means that we believe 90% of men matching this description to be a librarian and 10% to be non-librarians, or in this case, farmers. This also means that 10% of the 400 farmers in the village could also fit the description of Adam. Meek and tidy. So 40 of them, 10% of the 400. Both librarians in town could potentially fit the description of Adam, so 42 people in town could fit the description of Adam, of which only 2 are actual librarians. So the probability of Adam being a librarian is 2 in 42, so 2 divided by 42, 5%. This means that there is a 95% chance of Adam being a farmer, even assuming that the description of Adam matches that of a librarian 90% of the times. Now, this result is for sure much higher than what our intuition would suggest. For this reason, it is always important to consider base rates. Our intuitions can be helpful in many ways, but when it comes to making inferences and predictions using more complex information, it needs to be calibrated. This is particularly true in many clinical, legal, and socio-economic contexts. Take a judge or a jury. They should never dismiss base rates as irrelevant, and similarly, when interpreting clinical results, one should always beware of the base rate and the base rate neglect fallacy. Now, we are finally ready to look at what I mean by good and bad stereotypes. I have just introduced base rates, and I showed how ignoring them can lead to wrong judgments. This is especially true when we think by representativeness and use a specific stereotype to guide our judgment or decision, ignoring the prior probabilities or base rates. So prior probabilities is another term for base rates. This was encountered in the first episode of this series, when I introduced Linda. You remember? We saw that thinking by representativeness means using a stereotype and reaching the wrong conclusion. In that case, the wrong conclusion was that Linda is a feminist. Or just now with Adam, using the stereotype of the librarian led us to believe that Adam was a librarian and not a farmer. So, the stereotypes in these two cases, have misled our intuition when we should have used the base rates or prior information. The paradox here is that stereotypes are themselves a form of base rate. We develop stereotypes in our mind because they actually help us make better predictions in many everyday life scenarios. Let me explain. If somebody asks me to spot an elderly lady in a crowd, and I'm looking for her, I will look for white hair. This stereotype is a base rate. The percentage of elderly people with white hair is considerably larger than the percentage of young people with white hair. As an example, if we were in Rome, say outside the Vatican, in the middle of a crowded square, seeing white hair would safely indicate an elderly person. Now, let's change scenery altogether. Just because we can, let's travel in time, right? Why not? So we are now in the early 90s, and we are at a punk music festival. You spot someone in the crowd with white hair. Would you still be very confident that they were an old lady? I think you would correctly reduce your estimate that the person was elderly by a considerable factor. This means that you would successfully and intuitively integrate another base rate in your estimate. The percentage of old people at a punk music festival in the early 90s was very low. Even if the base rate of old people with white hair is very high, you still would want to get close to the person and find out if an old lady really did make it to a punk festival in the early 90s. The white-haired person at the concert could be elderly, but you wouldn't bet the same amount of money on it that you would if you were at the Vatican, like in the first example. Right, so this all seems very straightforward because our intuition guides us there. But we have seen that our intuition will ignore base rates when it comes to other situations. Why though? Let's see another example, this time by Daniel Kahneman. In a city, 85% of cabs are green and 15% are blue. After a hit-and-run accident, a witness says the cab was blue. So a test is performed simulating the conditions at the time of the accident. And it is established that the witness can correctly spot the color of the cab 80% of the times. Now, what is the probability that the cab was blue? It is very tempting to say that we are up to 80% sure that the cab was blue, because that is how accurate the witness is, and they said it was blue. But that would ignore the base rate that we have, which is that only 15% of cabs in the city are blue. So the correct answer, the probability that the cab spotted by the witness was actually blue, is 41% if you work out the math. Let me break this down like we have done before. Out of 100 cabs, 85 are green. The witness will recognize 80% of these as green and 20% erroneously as blue. So 17 of these 85 cabs are false blue. Out of the 100 cabs, 15 are actually blue. So the witness will recognize 80% of these as blue and 12 as real blue, because 80% of the 15 is 12 real blue. The total blue cabs spotted by the witness in this experiment are 12 real blue and 17 false blue, so 29. The percentage of real blue cabs out of all the cabs spotted is 12 divided by 29, so 41% of the times the witness is correct. The base rate tells us that there are many more green cabs, and we should not ignore that. There is nothing different in this example from the breathalyzer or the disease test that we have done earlier. But the interesting aspect comes now. Now, suppose I framed the problem differently. I worded it differently. And I said, in the city, there are equal numbers of green and blue cabs. But green cabs are involved in 85% of the accidents. The witness identified the cab as blue with 80% accuracy. So the witness has the same accuracy before, but this time I framed the whole thing a bit differently. I said green cabs are involved in 85% of the accidents, but there are equal numbers of green and blue cabs. The problem is actually mathematically the same, but Kahneman showed that intuitively we do not ignore the base rate anymore. He explains it by saying that we do not ignore a base rate if it seems causal, or if it seems that it's causing a specific effect. But later studies after Kahneman have showed that it is more general than that. We do not ignore base rates when they simply seem relevant. In this case, knowing who causes the accidents, which cabs cause the accidents, seems relevant. And as a consequence, we form a stereotype of the green cabs as reckless. So even if the witness says the cab was blue and the witness is 80% accurate, we still think that it could have been a green cab, and we adjust our judgment accordingly. By contrast, knowing how many green cabs are in the city seemed irrelevant intuitively, so our intuition tends to ignore it, leading to mistakes in our judgments. Sometimes a stereotype helps in making a better prediction. Just like when we were looking for white hair to spot an old lady in the crowd, sometimes the stereotypes mislead us, like in the case of Adam, the farmer who likes poetry. And sometimes we ignore base rates altogether, like in the first example of the blue and green cabs, where we tend to ignore the fact that there are so many more green cabs and only consider the accuracy of the witness. And this is what I mean by good and bad stereotypes. Of course, many stereotypes can be bad in other ways because they create false judgments against people or people who belong to a certain class who do not necessarily fit a stereotype. And this is why society and institutions have been progressively fighting against these stereotypes, even if at the cost of accuracy of judgment in many cases. Once again, this is a way in which our intuitive thinking, or our common sense, has evolved to our advantage, but in a natural environment. And it can go against our good judgment when it comes to dealing with slightly more complex matters, which are typical of the modern world. Using base rates correctly can lead us to making not only better judgments, but also superior predictions about the future, which will be the topic of the next episode. Right, so if you have made it this far, well done, because lots of numbers have been thrown around today, but I literally simplified it as much as I could. Trust me on this, a little numeracy goes a long way in interpreting the world, so it is always well worth the effort. And now I think it's time for me to have a snack and then go to sleep. Thank you so much, and bye for now.